Hello, welcome to our webinar, HALT Testing Effectively. Thank you for joining us today. This webinar is being given by MET Laboratories. MET is a leader in the testing of electrical and electronic equipment for environmental hardiness, product safety, and electromagnetic compatibility. MET operates world-class labs in Baltimore, Maryland, Santa Clara and Union City, California, Austin, Texas, and also runs operations in China, Taiwan, Korea, and Italy. This webinar will run 30 to 45 minutes with an additional 15 minutes for questions and answers. Due to the number of registrants, all attendees will have their phones muted. If you have a question, please type it in the questions area of your control panel. We will attempt to answer all questions at the end. If you are having technical difficulties, you can contact us the same way or call us at 410-935-6053. That's 410-935-6053. And we will try to resolve any problems quickly. Just a quick note on another upcoming event. Next month, MET will be hosting our big annual Global Compliance Seminar and Crab Feast in Baltimore. Register for this or other upcoming events on our website at www.metlabs.com. Today's webinar is being presented by MET's Tamlin Franklin. Tamlin has more than 13 years experience in environmental testing and has conducted HALT and HAS programs throughout the U.S. and abroad. At this point, I will hand over the presentation to Tamlin.
Thank you, Barnaby. Good afternoon, everyone, and thank you so much for your time today. We appreciate your attendance at this webinar. This webinar is an introduction to HALT and how to test effectively for the beginner. It can also serve as a way to fill in the gaps for those who may be intermediate or expert HALT engineers. What we hope to do today is to identify or define what HALT is, discuss why it's beneficial, and if you are preparing to perform HALT, we'd like to give you the do's and don'ts of what it takes to be fully prepared to get the most out of the process. And as we begin, again, I'd like to say thank you again for your attendance and welcome. For all those folk who are in the testing industry, if you will, I'd like you to think about traditional testing, if you will. And with traditional testing, there's always the goal of simulating some environment. We try to duplicate what the sun does by solar radiation testing, or we try to simulate the rainforest environment with high temperature and humidity testing. Or we may try to simulate the vibration a product could experience on a ship or the vibration in a UPS truck using an electrodynamic shaker and a random vibration. So in the traditional world, testing involves simulating an environment, and with the goal being for the product to get through the test program unscathed and hopefully with zero problems. What I've seen in the test lab is that customers come in and they hope and pray and have their fingers crossed throughout the entire program, hoping that there are no power supply issues, no data issues, or any electronic component issues. Now, for the sake of this webinar, I want you to take that information that you already know about traditional testing and just put it on the shelf in your mind, if you will. Because HALT is a different process altogether. HALT is a process that uses 3 major stimuli to test the product well outside of its normal limits. The stimuli used in HALT include extreme thermal temperatures, extreme temperature cycles, rapid thermal cycles, and vibration. And again, traditional testing would require hundreds or maybe thousands of hours of testing as opposed to a HALT test or process that can be completed in typically 2 to 5 days, but the average time in the test lab for our product is 3 days. HALT is an acronym for Highly Accelerated Life Test, and it is a design engineer's tool, and it is used to help the design engineer detect any process or design flaws early in the product life cycle. And if used properly, it can save substantial amounts of money. And it can also help the design engineer introduce a reliable product into the market. Now, the information gathered in HALT is used to develop screens that are used for what we call HAS. The information gathered in HALT, we determine the operating limit for the product and the destruct limit for the product. We use those limits to develop a screen for the product that will eventually be in the manufacturing arena. So once the product goes to manufacturing, the HAS screen will help to weed out any latent defects with the process. So the end consumer will get a reliable product. So HALT will take care of the design issues, and HAS will take care of the process issues typically found in the manufacturing process. Now, many types of products undergo HALT, and the list shown here is not inclusive, all-inclusive. It does list quite a few products that we've tested: automotive, medical, telecommunications, and you can see the list goes on. So there's no limit to what you can test. You can test a subassembly up to a full assembly of a product. The equipment used in HALT is shown here, and the type of chamber used is manufactured by Qualmark Corporation, and Qualmark has a series of Typhoon, HALT, and HAS chambers. This particular chamber is an OVS 2.5, which means it has the table dimensions are 2.5 feet by 2.5 feet. What you can see here on the chamber is that it has 2 access doors. One here you can see, and on the other side here where my mouse is the other door that's partially open. The chamber is also equipped with access ports, which are on the side to route cables in and out that will go to the product. And there's a window where you can see the product while it's under test. What the chamber affords is a temperature range from minus 100 degrees C to plus 200 degrees C. It has ramp rates of up to 60 degrees C per minute on the product, and it's equipped with vibration hammers that introduce a repetitive shock in all axes simultaneously across a really wide band from about 10 hertz to 5,000 hertz. So with that kind of temperature and vibration excitation, the product is tested well beyond what it would normally see to stimulate failures so that we find the failures before the customer does. Here's an interior view of the chamber, and you can see both doors are open, the rear door and the front door. And again, you can see the access port for the chamber. You can see the table hole pattern, which is 3/8 inch threads on 4-inch centers. There's also the view of the access window here in the access port, and these are the fans to route the air on the product during the test. What's not shown is the ancillary equipment that may be necessary. We use thermocouple meters, accelerometers, data loggers, oscilloscopes. We use different pieces of test equipment to monitor the product while it's under test. Typically, the customer supplies the support equipment, but the test lab will also have support equipment to help with the process. The next slide is very important because this is how the excitation is really achieved. With the omni-axial vibration, all axes, all rotational and linear axes simultaneously, the product is excited, and those latent defects or design flaws that would otherwise go undetected are able to be found with this type of vibration, which is really phenomenal. So why perform HALT? If we have to undergo a traditional test program, why do we need to incorporate HALT? Well, as you'll see on a few slides a little later, HALT is a quick and easy way to discover design and process flaws. It's also a designer's dream. Although designers are very crafty and they are brilliant people, sometimes the designs need to be improved, and this is a quick way for designers to use this process to help them improve and evaluate their design margin. And because the process is so quick, it's an excellent way to reduce development time and cost. If you had the opportunity to test in 2 days as opposed to 10,000 hours, I think most people would choose 2 days because it's so quick, and it's a process that affords you the opportunity to find the problems before the product is released to the market. And oftentimes, a product has a release date that it is almost impossible to meet. HALT is an excellent option because it will help to find the problems in the product before the manufacturer release date and maybe increase the time to market. Also, HALT can be used as an ongoing tool to evaluate revisions in a project or product. So if a product has undergone several revisions, then HALT can be used as a sustaining engineering tool to help evaluate each revision. An anonymous customer provided some information, and they said that finding design weaknesses as early in the product design cycle as possible can save substantial amounts of money. If the problem is found in the design phase, the cost is minimal. But as you can see, after before procurement, the costs increase slightly. And before production, they increase even more. And if the problem is not found before shipment, or if it's found before shipment, you can see what the costs are. But if the problem is not found until it reaches the customer site, the costs are exorbitant. This is probably the most important slide of all because this shows the cost for actually not performing HALT. And as you can see, the x-axis represents time and the y-axis represents the spending rate for a product. And in the traditional world, the costs ramp pretty quickly and then plateau until the product undergoes design verification and then is released to the market here at 12 months. Let me go back. After the manufacturing release of the product is in the field and it may encounter some failure. Once that failure is encountered, then warranty costs come into play, support personnel have to be sent out into the field, and that is represented by this blip here on the chart. This could be at a higher spending rate. We don't know. But nevertheless, there are additional costs associated with the product after the manufacturing release. Now with the HALT model, we can see that, represented by the dark blue line, that there is still some initial spending with the product because it has to undergo some traditional testing, but there's additional costs associated with HALT, and that's represented here with the green box. So after the initial spending, what HALT affords us is an earlier manufacturing release date. Actually, the product could be released 2 months sooner than it would with traditional testing. So HALT affords us the earlier manufacturing release date, shown here at 10 months as opposed to 12, and the additional spending came about 8 months into the program. And as you can see, after the release date, the spending has almost dropped to 0. So the savings of performing HALT is represented here by the shaded area. And that's one of the major reasons why HALT should be performed, because in the long run, it's going to result in substantial savings. The HALT process involves test plan development. This is where the HALT engineer sits down with the design engineer to discuss all the parameters of the test. Which product will be tested, which revision level, what are the test nodes, what functional equipment is needed, what constitutes a failure, and we begin to discuss fixturing as well in this stage. We also determine the need for ancillary test equipment. Again, are we going to use an O-scope to monitor the unit while it's under test? We just need to identify those things beforehand before we get into the HALT process. And verify the functionality of the unit. Because HALT is an operational test, we have to determine the method that will be used to monitor the product and operate the product throughout the test. And then we would run the HALT. And in the process, any failures that are encountered need to be determined. The root cause of the failure should be determined. So failure analysis needs to occur as well. And then any corrective action that can be implemented should be implemented, and it shouldn't be ignored, because those failures that surface in the HALT process will surface in the field if they go uncorrected. And then after corrective action, so if you made any changes to the product to maybe secure a component that was dislodged, or you changed the epoxy or did some other corrective action to the product, you want to make sure that what you introduced or what you corrected did not actually introduce new problems into the product. So a repeat of the HALT process would be necessary. And that's the correct way to actually conduct the process to get the most out of the test program. And again, ongoing evaluation. If there's a revision to the product, if there are changes, then each change needs to be evaluated. Now, HALT incorporates the step stress process. And step stress testing is simply testing at a level and then increasing the stimuli in an incremental fashion after performing a dwell at each level. So we start at an ambient temperature, for instance, for thermal, for cold step stress testing, and then we increase the temperature in 10 or 15 degree increments until we reach the operating and destruct limits for the product. The operating limit for the product is the temperature before any characteristics of the product are out of spec. And the destruct limit is the temperature at which one or more of the operational characteristics of the product are out of spec. So the operating limit is the temperature prior to a failure, and the destruct limit is the limit where the product experiences a failure and does not recover. This slide shows all the stimuli that the product will see during the HALT process. We begin with the cold thermal step, and we move in a counterclock direction, if you will. We start with the cold thermal step, then we continue with hot thermal step, and we test the product and monitor the product throughout the process. We apply additional stresses. That could be voltage margining, frequency margining, power margining. We apply additional stresses, and then the 6 degree of freedom vibration, and then a combined environment of temperature and vibration. So this is the process in a nutshell. So again, the HALT process starts with the least destructive step, which is the cold thermal step. It then moves to the hot thermal step, vibration followed by rapid thermal transition, which uses the limits found in the cold and hot, and then the combined environment of temperature and vibration. When a failure is found in HALT, it should not be discounted or ignored. Each failure during the test program should be analyzed. So if a failure occurs at, say, 50 degrees C during the hot thermal step stress, then we should stop the test, record that failure and the stress level, and try to isolate that problem using a microscope or any other isolation technique to determine what the failure was, the location, and possibly why that component or why that failure occurred. Document the failure location and determine the root cause analysis. This is another reason why we sit down with the design engineer and we really press for the designers to be present during the HALT process, because they can help in this area, and that will cut down on time as well. Because if the design engineer is not present, then the unit or the product under test may have to be sent out for further evaluation to a FA or failure analysis lab. So we typically ask that a design engineer be present to help determine the root cause of the failure during the process. So a failure can be encountered at 50 degrees C, and then the same failure could be encountered during vibration. So the design engineer would help to investigate that failure and determine the root cause. And if possible, they can implement a fix at that time. It may include something very simple as epoxying a component back to a board, or changing the data rate for the program. So the fix on the spot is really what we desire, so that we can continue testing and hopefully stimulate more failures, because cumulative failures are good in HALT. We hope to identify as many failures or flaws as possible during the process. Failures are good. And then we continue testing again to find any additional failures during the process. This next slide shows the results of products tested on the West Coast, and it shows the percentage of failures induced by each stimuli. And as we said earlier, the process is the same each time HALT is performed. We start with cold thermal step, low temperature, then high temperature, then rapid temperature cycles, vibration, and then the combined environment. This pie chart is very important because after the first 4 stimuli are introduced, we can see that the 5th step in the process, which is combined environment, still identified 20% of the failures for the products tested. And this pie chart represents 47 different products from 33 different companies and over 19 industries. So the failures found, we'll see on the next chart, include power supply issues, cold solder joints, nicked leads, drifts in capacitors, and tolerance issues. And this list, again, is just some of the issues that have been found with using the HALT process. Now, we tested a product a while ago, and it was a battery charger. And what the customer found out was that the unit was having intermittent failures in the field. Customers were complaining that the units were failing. They didn't know why. There didn't seem to be a rhyme or reason for the failures. So because the product was mature and in the field, the customer opted to use HALT. If HALT had been used previously, then the customer would have been undergoing HASS and hopefully would have identified these issues. But we can see with the HALT that they identified a problem. What happened was they were using two different manufacturers at two different factories. The product was being manufactured at two different locations. One factory changed the soldering process, and they did let the customer know, but the customer wanted to fix the problem and was pressed for time, and they wanted to know if maybe that process change was the cause of the failures that they were experiencing in the field. And they wanted to know if HALT would be able to duplicate those failures. So they opted to bring both units into the lab, and they wanted to determine if maybe the soldering process was the culprit. So what they did was they brought two samples into the lab. They brought a good sample size of each unit, the units with the questionable solder and then the original units that had no soldering issues. They supplied over a dozen samples for each unit. The samples were tested, and again, we start with the cold thermal step. So the sample started at 20 degrees C, and we stepped down in 10 degrees C increments, and we performed a well, verified that the units worked, and then at minus 50 degrees C, both units were still operational. Well, at minus 60 degrees C, the next step in the process, one of the samples stopped functioning and the other began operating erratically, but it fully recovered at ambient because remember, we stopped to identify the failure at each step. So if a failure is encountered, we stop, we go back to room temperature, we try to determine what caused the failure. What the customer found with their failure analysis was that a Hall sensor was the suspected erroneous component. And further analysis was conducted on both samples at the customer site. What they reported to MET was that they discovered 10 whiskers on 100% of the samples that had the questionable solder, and none of the samples with the original solder had any. So what was their corrective action? Naturally, to discontinue production at the manufacturing facility with the new soldering process, and to go with the manufacturer with no solder process issues. Another test case, we had an electric meter that underwent HALT. And this unit was under constant revision, but after each revision, the customer opted to perform HALT. And this particular time, they wanted to determine if the most recent revision resulted in a more robust product. So again, we test the units side by side, revision 1 next to revision 2 simultaneously. And in this case, temperature testing yielded no anomalies. However, during vibration at 20 GRMS, both units operated, again, with no anomalies. but at 30 GRMS, one of the units lost power and did not recover. In the other unit, there were no anomalies observed. The failure analysis conducted by visual inspection on site revealed that 2 capacitors had dislodged from one of the units, and the other unit had obviously had some changes made where those capacitors were still intact. So corrective action was the customer confirmed what they believed, that their newest revision was more robust than the previous, and they continued to utilize HALT for new products and each revision of existing products. Now, based on what you've heard, HALT seems like a good idea. And if you want to move forward with HALT, preparing is paramount to a successful program. It's always necessary to decide or determine what engineers need to be present. Again, we always ask that a design engineer be present because they are most familiar with the product. And if a design engineer is not able to be present, someone else who's familiar with the product should be to help aid in the process. Also, list the major functions of the unit that will be exercised and monitored during the process, because a non-functional sample during HALT will not yield the results that an operational sample will. So the goal is to operate the unit fully and test and monitor it up to hopefully 100% of the functions of the unit during the process. And again, we have to identify what equipment is necessary, what ancillary equipment is necessary, what nodes need to be monitored, where will we place accelerometers, where will we place thermocouples, and the like. What constitutes a failure? That needs to be identified up front. If a tolerance level shifts, will that constitute a failure? If a red light turns green, will that constitute a failure? It needs to be specified up front what constitutes a failure. Again, how will the unit operate while it's in the chamber? We need to provide at least 5 feet of cable from the product to the test bench outside of the table. Identify any thermal shutdown circuits in the product and confirm first that they work, and then decide if there's a way to bypass them to continue testing. Because if there's a thermal shutdown at 60 degrees C, then the unit would naturally not work beyond that temperature. So we want to bypass that shutdown and continue testing as high as we possibly could. Again, how many units will be tested? This needs to be determined up front. If the units are relatively small and are readily available, then more than one may be tested at a time. But if there are not many units available for the test process, then maybe spare parts are available, and we need to determine how many, if there are. And also, are all the units of the same revision level? Imagine testing a product and testing 3 different revs of a product, but you thought that you were only testing one, or the most recent. That may pose a problem with your results. Again, what specific cables are needed? Can sensitive modules be located outside the chamber, such as LCD displays? Because we know that at high temperatures, the LCD display will turn dark and be unreadable. So we may need to find a way to isolate those modules during the test program. And if possible, we ask for a non-functional sample so that we can develop the fixture, which is typically a lightweight and low-cost fixture, but nevertheless a fixture for the product while the product is undergoing vibration and the combined environment. So preparing for HALT is just as important as the HALT process itself. And preparing will afford the most benefits. And again, if you opt to subject the product to HALT, which is a stimulation product and not a simulation process, the benefits gained are many. For one, you save a lot of time, and the biggest one, I guess, is the amount of money that can be saved. The cost savings is substantial. You can possibly introduce the product a little sooner to the market. You introduce a product with minimal process weaknesses or design weaknesses. You increase the out-of-box quality. You conduct the process in a quick and efficient fashion. And the overall process just yields a faster time to market at lower cost. And with that, we thank you again for your attendance. And at this time, if there are any questions, please send them now.
Thank you, Tamlin. I wanted to mention that this webinar will be available on metlabs.com, and we will send an email to everyone with a link to it. As Tamlin said, now we will answer any questions. If you have a question, please type it in the questions area of your control panel. Joining us now to help answer questions is Troy Franklin, Director of MET's Environmental and Energy Laboratory. Give us just a minute here to get organized for questions.
Our first question is, how do you determine the rate of change for extreme temperature cycles? Is this a step stress as well?
The rate of change is dependent upon the mass of the product and the rapid thermal rate of change for the chamber. The chamber can achieve up to 60 degrees C per minute, and we program the chamber to achieve that, but the mass of some products will preclude that rate of change.